All right, chapter 5, section 4, the geometric and the Poisson distributions. So these are going to be two different distributions, but it's going to be working with the same sort of logic that we've already been working with, that you're going to have a probability of success or an average, and we're looking for the probability of something happening. So we're going to be using Google Sheets, and we're still going to be answering the same types of questions. They're still going to ask you things like, what's the probability of 2 successes, or at least 2 successes, or no more than 2 successes. And so it's going to be the same general logic that we've been working with. So that's kind of a relief going into these distributions. The challenging thing is just recognizing that it's happening. So just to recap the 2 distributions we've done so far, we just did a basic probability distribution. That's when you were given a table of values and the probability of each value occurring. And in order to find the mean and the standard deviation, the mean was every x value times the probability, and then we added them all up. The standard deviation was taking every x value minus the mean, squaring it, then multiplying it by its probability, adding all those up, and then taking the square root of it. So that's when we had to build that little formula in Google Sheets. Then we moved on to the binomial distribution, which we knew was the binomial distribution because there was a probability of success and failure, and it reoccurred, and the probability never changed per event. So if there was 80% chance of success, if you succeed once, it doesn't change your probability. And it could repeat as many times as we wanted. So we could have any number of successes out of a finite number of trials. Where the geometric changes is the geometric stops after our first success. So the distribution ends at some point. And what we want to find out is the probability of failing a certain number of times before we succeed for the first and only time. So with the binomial, we can keep on succeeding, we can keep on failing, just repeats over and over and over again. The geometric distribution, we fail every single time until we succeed, and then we stop with the problem. So you're going to know that it's geometric because the question is going to be asked, what's the probability that we succeed on the 5th try? So you're stopping after the 5th try because we're assuming that you have succeeded. Now the formula we're going to be using is right here. It is the probability of success times the probability of failure to the power of n minus 1. The logic is that let's say you succeed on your 2nd try. That means you failed and you succeeded. So those probabilities we would multiply because it's an and statement. The failure happened once, the success happened once, so it's just success times failure. If you succeed on the 3rd try, that means you failed and you succeeded. So that's, you would have 2 failures and 1 success. So since you're always succeeding just once, that's why it's to the power of 1. And since you're going to fail every other time, that's why it's to the power of 1 less than the number of times you're trying. If you succeed on the 1st try, 1 minus 1 is 0, and q to the power of 0 would just be 1. So the probability of failure would then go away. So n is the number of the trial on which the first success occurs, and p is the probability of success. And yes, the probability of success is going to stay the same for each trial. The formulas for the mean and the standard deviations. This being mu, that's the population mean. We can also see it as x bar, but this is the expected number of times you would want, or that you the expected number of times you expect to try something before succeeding. So if passing a class had a certain probability of success, how many times do I expect to fail the class before I pass? And then once you pass the class, you're not going to keep taking it because you would have already received the credit for the class. Sigma is the standard deviation. So you would take the square root of the probability of failure and then divide it by the probability of success. And you'll notice that in the Google Sheets, under the geometric distribution, we will be doing the mean and standard deviation as well as answering a few of these questions. The 1st try, the 2nd try, those are exactly 1st or 2nd, more than 3, 1, 2, or 3. Those are all going to be kind of the cumulative probabilities. And we're going to do that based off of this example here. So an automobile assembly plant produces sheet metal door panels. Each panel moves on the assembly line, and as the panel passes a robot, a mechanical arm will perform spot welding at different locations. So each location is set by a magnetic dot, and basically the robotic arm has a sensor. It looks for that magnetic dot, it finds it, does a spot weld, and it moves on. But as we know, nothing's perfect. In fact, this one is only 85% successful, and that would be locating the magnetic dot, making the spot weld, and letting the door move on. Now, if it's only 85%, then you probably want to give it enough time to try once or twice or 3 times or 4 times or 5 times or however many times you want in order to have a higher probability of it being successful. But it's an assembly line, so you don't have someone sitting there saying, yep, weld's done, and then moving along. It's set on a timer. So they want to have this so that there's enough of a chance or enough time to give this robotic arm a chance to make the weld, but not too much time that you're wasting money. Because the more time you give this robotic arm, the less doors you can produce. The less doors you produce, the less money you're making. If you don't give it enough time, then you're going to have more defects and recall, and that's also not good. So you have to find what is that middle ground. And then when all these doors have been welded, that you probably have some sort of technique, maybe like a systematic technique where you're picking every 100th door or something like that. So let's go ahead and start just doing the work that we're going to need to do in order to be able to answer some of the questions. So in the sheet, put in that the probability of success is 85%. That means I know the probability of failure is 15%. My formula is going to be P times Q to the power of the number of times I fail. Again, it's n minus 1. So what I recommend doing is set a table like this. Now, I know that I only need as much as 3, but I wanted to just do more tries because I want to show you the probabilities and how they're connected. So I just typed in the number of tries. So I tried once, twice, 3, 4. I'm going to try 8 times and see what the probabilities will be. Now, for my probability of success, again, I am going to use this formula. So I'm going to do equals my probability of success, which is 0.85. And I'm going to multiply it by my probability of failure, which is 0.15. And I'm going to put it to the power of. So again, that's going to be shift 6. And now I don't want to have to type in the number of fails every single time. So that's why I created this column, because I can now just click on this cell, hit enter, and I know that this probability of success is 85%. But now I'm going to grab this blue square, drag it down, and what it just did is it took every single probability of failure and changed my exponent. So that is all the work that you have to do ahead of time. You are now able to answer all the questions. Now notice the probabilities. Now some people start to wonder, well, if I'm going to try twice, my probability of success went from 85% down to 12.75%. So why is it that I have only a 12% chance of try number 2? Well, that's because it's saying that there's a 12% chance that you would have failed the first time and then you would have succeeded. So there's a slim chance of that happening. So as an engineer, I may want to say, well, what's the probability of trying once or twice? So what we're really doing is we're going to be adding these numbers together to find our cumulative probabilities because we want the first or the second try. So yes, the probabilities do decrease because it's highly unlikely, like number 8 here, there's a 0% chance almost of trying 8 times before you get that first weld, given that there's an 85% chance that you'll get it on the first try. So if I want the answer for the probability of the first, I would just use 0.85, so cell C7. On the second try, that would be 12.75. If the question asks the first or the second try, then that means that I want either this one or that one. So since it's or, I'm adding them together. And I get that if I were to give this robot enough time to do 2 tries. So it can try once and it can try twice. There's a 97.75% chance that it will make that weld. If I wanted to give it more than 3 tries, again, more than we can't calculate because I would have to keep doing this an infinite number of times to get all those decimals. I can't do that. I don't want to do that. But what I can do is calculate everything that I don't want and subtract it from 100%. So if I want more than 3, that means I don't want 3, 2, or 1. So I am going to go ahead and take 3 plus 2 plus 1, get this really high probability, and I'm going to subtract it from 100%. I'm going to subtract it from 100%. There we go. Now you'll also notice that I have to put the parentheses because order of operations would have done 1 minus cell C9, and then it would have added the other 2 to it. So make sure that if you want to do a more than and you're doing a sum of something, either use the sum command or make sure it's in parentheses. So this is saying that there's about a 0.3% chance that it will take more than 3 tries. Is that enough to risk what's going on and missing a weld? I would say, yeah. I would say if you give this robot enough time to maybe try it 1 or 2 or 3 times, so 1 or 2 or 3, there's a 99.66% chance that the weld will happen. And so as an engineer, I'd probably program that station to give the robot 3 tries. It makes the weld, all right, it just stays there and waits for the time to go out. Otherwise, it searches, tries, and there's a 99.66% chance that the weld is complete. How many tries should we expect? So what would be the average number of tries? Again, that is 1 divided by the probability of success. So 1 divided by 0.85. You should expect the arm to need 1.2 tries. So you're expecting it to be a little over 1 try, so you could probably even get away with letting it do it twice, but is 97.75% enough? That's up to you and the business. The standard deviation is going to be the square root of Q divided by P. So the square root of my probability of failure, which is 15, divided by the probability of success. So there's a 1.17 as the mean, give or take about a half a try. So that's what kind of boosts it up into kind of close to 2 tries than to 1. That is the entirety of the geometric distribution. Again, I know it's geometric, so I'm stopping after the first try. I have to create my formula. I would recommend creating this table. Knowing that the question said 1, 2, or 3, I didn't need to go to 8, but as you saw that once you set it up, it's just doing it once and then grabbing that blue square and get down. So there really was no harm in doing more trials and failures, but it was unnecessary. But once you do have these values, then it's just clicking on the cells, and it kind of goes back to a probability distribution where you just look table and then use the probabilities. That's kind of what we did based off of the geometric information. Does anybody have any immediate questions? Again, I will kind of review this relatively quickly tomorrow and then let you guys try a few problems. So today is not really a practicing day, it's just kind of a basking in the greatness of the geometric and Poisson distributions. All right, on to the Poisson distribution. So how we know we're going to use the Poisson distribution, and this formula we do not have to use, by the way. It looks pretty intense. You have some factorials in there. We have this new Greek symbol that looks like an upside down Y. That is called lambda. Lambda is used whenever we have averages. Now, if you take a statistics course in college, the Poisson distribution is focused on a lot. They use this one because a lot of times with information, you may not know the probability of success, but you do know the expected number of times to succeed. Usually this expected number is over an interval of time or space or volume, such as how many earthquakes you expect over the next 10 years, given that you have 3 every year, something like that. So what's the probability of having more than 10 earthquakes? Or you're talking about fish in a pond. What's the probability of catching so many fish over a 6-hour period, given that you're traditionally expecting this many fish? So they're going to give you an expected number, and it will always be associated with time or space or something like that. The reason why they do that is that we may need to change that value to make it applicable to what the question's asking. So if you expect to catch 1 fish every hour, what's the probability of catching 10 fish over 6 hours? Well, you'd have to change your lambda because we're no longer expecting 1 fish per hour. We'd be expecting 6 fish per 6 hours. So we'd have to change the lambda based off of what the problem is. And we'll be doing a problem that kind of goes over that. The population mean is going to be lambda. So whatever they say is lambda, whatever we calculate, that's going to be our mean. The standard deviation is the square root of that lambda. Now down here is a technicality that they're saying that with the Poisson distribution, that we can use it to approximate the binomial distribution by just taking n times p, finding the expected value, then using that as our lambda. The reason why that's in there is, as I said, the Poisson distribution has a heavier focus in more advanced statistics. This is the only time that we're going to be talking about it. If we made it to further chapters in the book, then they bring lambda and the Poisson distribution back, but we're not going to be exploring it past this chapter. So that's just kind of a little disclaimer in there. It's nothing you have to worry about, but mathematically speaking, it is important. It's just not going to be important to us in this class. All right, so I'm going to paraphrase a problem that's in the book. It's talking about going to an Indian reservation, and there's a lake called Pyramid Lake located in Nevada. And the lake is described as a love jewel in a beautiful desert setting. But in addition to its natural beauty, the lake contains some of the world's largest cutthroat trout. I mostly just like the name, a cutthroat trout. These cutthroat trouts are pretty big. It's not uncommon to catch a 12 to a 15-pound trout. And so people come all over the world to fish at Pyramid Lake to try to catch one of these cutthroat trouts. Now, obviously, you're not going to really make the journey unless it makes sense to do so. So they said that usually you should expect to catch 2/3 of a fish per hour. So that would be 0.66666 or 0.667 fish per every hour. What I want to figure out is what's the probability of catching 0 fish, 1 fish, 2 fish, 3 fish, or 4 or more fish. Now, what they also say is that when you decide to fish at Pyramid Lake, you can kind of go out for the day. So let's say you were to go out for 7 hours. What's the probability of catching 0, 1, 2, 3, or 4 or more fish if you're on a 7-hour fishing trip? So that's all the information we need at the moment. So I went ahead and I started to put in some questions and some information. So we know the current lambda, which is per hour, is 0.667. But I'm not going to go on a 7-hour fishing trip and expect to catch less than a fish. If I'm expecting 2/3 of a fish, thank you, per hour, how many fish do we expect in 7 hours? And so what I'm going to do is I'm going to take that 0.667 and multiply it by 7. Because if I'm expecting 2/3 of a fish per hour, I'm really expecting about 4.7 fish in 7 hours. Now I do this because the problem is living in the world that we are on a 7-hour trip. So when I use my lambda, I have to use this 4.669 number, not the 0.667 number, because all the questions in the problem are dealing with a 7-hour fishing trip, not a 1-hour fishing trip. So what's the probability of catching a fish in an hour? So that means I'm going to use this lambda. So to do this command, I'm going to start typing in the Poisson distribution. All right, it's going to be difficult. And I'm just going to type in the word Poisson, and we are going to use our x value, the mean, which is our lambda, and then whether or not it's cumulative. So again, that goes back to the true and false that we did with the binomial. So since we want a fish in an hour, then that means that we want one fish. We are expecting 0.667 fish, and I'm going to type in the word false because that means I want exactly one fish. So there's a 34% chance that would catch one fish in 1 hour. 4 fish in 1 hour. The Poisson of 4 fish, it's still an hour, so I'm still expecting 0.667 fish. And again, I'm going to type the word false because I want exactly 4 fish. So there's almost a 0% chance of catching 4 fish in 1 hour, given that you only expect to catch 2/3 of a fish. How about at least one fish in 7 hours? So at least one fish would be 1 or 2 or 3 or 4 or all the fish in the lake, which we don't know how many there are. So since I don't know how many and I can't count up, I'm going to calculate everything I don't want and subtract it 100%. So I'm going to do 1 minus the Poisson distribution. And if I want at least one, that means I don't want to just not catch any fish. The expected number, again, we're gone for 7 hours, so now I'm going to use the 4.669 number. And for this one, the false and true doesn't matter because counting down from 0 or at 0 would be the same thing. And so there is a 99% chance that if you go out for 7 hours that you're going to catch at least one fish. So as a business, if I made that guarantee or your money back, knowing there's a 99% chance that you're going to catch at least one fish. So if I said to these people, yeah, come on out, and if you don't catch a certain number of fish, I will refund your day's trip and we'll give you an extra day out on the boat, something like that. Knowing there's a 99% chance that you're going to catch one, do they know that? No. And it'd be pretty exciting that if you, I mean, I don't fish because I think it's boring, but if you're going to catch a 15-pound trout, like you only need, I guess, one to kind of make it worth it, but I don't really know. Like I said, I don't fish. All right, catching 4 or more. Again, the or more is counting up, so I want to figure out everything I don't want. So if I want 4 or more, that means I do not want 3, 2, 1, or 0. So I'm going to do equals 1 minus the Poisson distribution. At 3, it's in 7 hours, so I'm going to use the 4.669. And now I'm going to type in the word true because I do want to count the 3, the 2, the 1, and the 0. And there is a 68.5% chance that you will catch 4 or more fish. So again, that's just good information as a business to know, well, here's what I expect to happen. Here's the probability of this happening. What are the pros and cons of the guarantees that I give? The mean, if I wanted the mean for 7 hours, again, that would just be the lambda and the standard deviation. I should have specified this for 7 hours would be the square root of lambda. So you take a group out on Pyramid Lake, and each person over 7 hours, you should expect them to catch 4.669 fish, give or take 2. So you're expecting them within 1 deviation from the mean to catch between 2 and 7 fish. That is the expectation. That is what probably will happen. Obviously, they can catch more, they can catch less, depending on the weather, all that stuff. So that is Poisson distribution. So quick recap, geometric, we stop after the first success. because we have achieved what we want to do. So that's how we know it's geometric. Poisson will not give us a probability of success. Instead, it will give us a known average, an expectation over a period of time or space.